You guys can find Dr. Patel's channel on YouTube. Just want to give you shout out to him, credit. I do have permission to use his information. So let's go with from him. Let's go with the video. Let's just jump in there. Reinforced concrete. It's let me jump to his experiment. You guys can come read the comments if you like. But we're talking about the FIU bridge, obviously, in context. Let's jump to, we'll look at a couple of his videos. That's just, that's obviously pre-stressed concrete. See, no tubes, and there's your cabling. And these are temporary supports. It does not state that, but these are obviously temporary supports after the fact because it would not have failed there in this plane. These would have been compressed. So if they actually did put 3 of these type of columns there. So this is after the fact, and these are the temporary supports. Interesting, it's on this side, and we don't see any over here. That's noteworthy. Let's go on. Tons of cabling, though, isn't it? It's wrapped with apparently a plastic sheet material. I'm going to go forward a little bit. Look how beautiful this image is. Now, does this not look like this could be, if you just pretend like this is a load on top of the bridge, but this would be the truss system of the FIU bridge, and this is solid, obviously. And this would be the pier, and this would be the 12 column, and that would be the 11 going here, and the rest. I'm sorry, the rest of the I-beam design they refer to it as. But you see where it breaks right here, falling away down, not pushing it off. Shear failure is in this plane. It could be in that plane if somebody was to push it back and this could not move. It would have to shear against these 2 members, would be the shearing members at that point. So you can see it break away. This would be the where it breaks away the deck. Let's see if I can get you jump to the video. So he does a video here. Back it up. No video, just a shot. Here's his point loads. If this is the dead load of the structure, the bridge, you would, and this is here, if cribbing is here to help him pick this up, obviously, when he's, after this fails. You don't want it on the floor to try to get it up. So this would be it, just to limit the failure, the falling of this beam. Again, there's your load point here, and this would be the dead load of the structure, in this case, the bridge, resisted by the pre- and post-tensioning of the cabling and some steel, minimum steel. Everybody talks about it needs more steel, needs more steel. There is no room for more steel, is there? It's like a 1 foot thick deck. There is no more steel allotment. You can't have giant stirrups in there all the way up because there's the way it's shaped. You can't get the stirrups up there. I think he has a stirrups video. Let me, so I can show you guys stirrups. Experiment set up for beam testing is what it says down below. You guys cannot see it. My screen recording is not large enough. So 100 millimeters, 400 millimeters, 100 millimeters. So it's not a big beam, but these are the stirrups. It would act like a stirrup if it was connected. And so kind of cool. Check it out. Let me fast forward it. Setup lab view for beam testing. All right. So C1. They're going to mark the cracks right now. But what I want you to note, and I've been really working on this very hard, diligently in the real world, finding locations before I do a video, but I'll give you a gist of it, is that when a structure is failing from shear, this is already a shear crack, it doesn't exhibit itself at the top that easily. This still looks pretty much in plane up top. You'll see the cracks, which I really like his video doing this. It's the only one I could find doing this. You see it doesn't go all the way to the top, so you don't see it. That's that inverted V I talked to you guys about. That if you can imagine it, this would be an open of the V, and that would be the point of the V. But look where it resolves itself. Right about there is where it transfers the load into the stress expresses itself in the crack up to there. And over on this side, it's like this. But it's a 45. See the 45? Remember I talked to you guys about loads, how they transfer on 45s. Well, I haven't found anybody talk about this in 45 papers or anything else. But you see the 45, and you'll see that now, since this cracked first, all bets are off. The load is now once you have this crack, now the loads are transferring differently in this structure. So over here, if you were looking at the structure, you see these two and you go, huh, might be failing flexurally and not under shear if it was more in center line. But you might be thrown by it. You don't see the cracks coming out this way because it's already on this end of the structure, it's already cracked first, and now the forces are redistributed differently and exhibiting in this format, as awesomely he shows with his penning. I hope he's not upset by my take on this. If he is, please, he can comment and tell me he doesn't like my take. And I'll leave it alone. Whatever he states, I'll leave it alone. I won't correct it or anything. I'll just do it. So now again, so as the forces are applied and we see they're developing now, the cracks are developing and literally developing with the guy's marker. You'll be able to identify some of them beforehand. So now it looks more like these are more the flexural cracks in the middle now as it's holding on. And here we go again. And they're developing. That same one's developing up. But look how far we're going before we're not even seeing any cracks at the top surface yet. So when you see cracks at the top surface, you've already screwed the pooch, right? You're already way down into the drama and trauma. So I don't know what the forces are on this at this point. But this looks all flexural at this point. You say, oh, it's flexural. But in reality, the shear developed first. And now the flexural part of this member is keeping this thing together. I would theorize that if he didn't have reinforcement across here, this would have already popped. This would already be on the ground. But look how far we got. This one looks like it went up a bit. Look how far we've gotten already, and it doesn't show it at the top. It does show bending, but not all the way through. Now here we're coming just about to the top. It looks like we made the top over here. Interesting, the loads, I guess, no longer migrate down there. It found another path that went on the outside. That's an interesting, but still approximately 45. Now we look at this one, and you see it's developed further up. And what does it look like? Now it looks back like a shear again, back to 45. So you see how elusive it could be but this one developed first. Once those forces are shown and then they start developing, it's this far before you finally see that the balance of the one to the left and the one to the right are what I'm calling shear force development. And here's your flexural development in the middle. I love this stuff. And out here, we've got nothing. We've got some compression going on, some outward compression. It's now freed, though. What's holding it now is a steel. It could be some tension out here. I don't know what the steel looks like out here. But what would stop it is the stirrups, imagine that the stirrups are in line with this marker here, that they're stopping it from pulling away, blowing out, because they're now the rebar the reinforcement is in tension and the diagonal format. Now we don't have diagonal format to protect it in the structure such as FIU, short of the down number 10 where we've got the bar, the reinforcement, the post-tension bar to help it in that capacity. But it's not solid as this member is, where you get to pick any location. I did read his comments. It's a 28-day cure, so it's well developed, well cured. And there we go, mimicking this one over here. This one came first. This one now is second, but it's getting symmetry. As you can see, everything's symmetrical. It balances out. All right, so let's follow it. But now we're at the top surface for sure. Now the cracks are showing through. And now we got compression a little bit down here. We're getting breaking of the concrete right here, where it's being bound into the other concrete that's bound by the reinforcement also. Coming into compression there, the concrete is, and it will break and fall down onto the table, as we see at the FIU collapse, we see concrete on the floor of the deck, and this would be the same thing as I theorize. And here we got some popping. See how it popped out again, the compressive point, as it no longer can compress anymore, it's got to give. So there's the bound up part, and it popped off. And it popped off just a moment ago. You can rewind it if you need to see it. Slow down the video. It is taking it though. Now up here, we've got our just full break, and here we go again. Look at it go though. Look at it travel. Looks like it's going to break this piece off if it could. If it's reinforcement, it's going to probably hold it. I don't recall exactly. But the symmetry, look at his lines. See the symmetry on it? It's beautiful. And now we're getting it bowing out, bubbling out, expanding forward. But we're now no longer in plane. Just like the FIU bridge, where you can stick a tape measure behind it now in the other direction, though. Just like that, we're starting to get that. Here we go. Here. Way beyond where it was in plane before. And it's shooting out again. We're no longer in alignment. And you're getting your pieces breaking out. They're just no longer being able to hold on the reinforcement in there. I'd love to be able to see it. Maybe it's in there. Maybe it's right there too. But now it's pushing down. The reinforcement is just pushing down on this, what's left of this concrete. Stirrups in here, I don't know. They would tie back up into there then and redirect, come back around full circle, if you will. That was okay, guys. So Dr. Patel asked me to share this with you. There's his details, Gmail, cnpatel.693@gmail.com. So please, and I'll share it below in the comments, but just wanted to make sure that was clear. Okay, with that said, let's jump into his Flexural video. Kind of cool video. We're going to look at that 45 thing again. I'm going to step it up. Let's look at, well, I'll give you his definition. Flexural strength is known as the modules, ruptures, let me pause it. Bending strength or fracture strength is a material property defined as the stress in a material just before yielding its yields in a flexural test. The highest stress experienced within, I was going to say without, within the material at its moment of rupture, without rupture, I'm going to say, it is measured in terms of stress. Okay? To overcome this type of failure, main steel is provided at the bottom and top of the beam. Flexural failure occurs at mid-span of beam. There are many causes of flexural failure. The flexural failure is governed by concrete crushing after yielding of the steel. And that was that I think he was referring to what I talked about with the compression of the concrete at the far right in that one video that just now. And it has nowhere to go, right? The steel is doubling back. It's still holding on each side of the crack, and it's still bending, and it's just coming in contact with itself across from the crack, and now it's crushing. And I think this is what he refers to as crushing after yielding of the steel. And remember, on one side, it's now pulling, so it's in tension. Fast forwarding. What we got here? Flexural failure, right? Shear failure. Here's the load, and here's the load. Okay, so here are the two load points. Okay. See the uplift here? See the negative load right here? As it goes down, it creates a negative load and a point load here, and not here. This will be the dead load of what I call the FIU bridge in the center, creating that negative load, but they never talk about it coming off of here. But perhaps Denny Pate's intention was to shim it under here to try to resolve some of that negative load. So there it is. These are more in line with the center of the span. And that's a roll and a roll pin. Okay. Wish I could see more of that one, but cool. And here's his another video of that. Here's your flexural. It is a point load, right? It's a plate. But I would love to see cracks off of here. I would love to see this go all the way to failure and off of here, and I'd love to see it from the start. We already saw one from the start. I would guess, though, how this developed was we're next going to look at his flexural demonstration of a different. Don't get confused with this last image. This is a new steel too, right? I don't know what the steel looks like in there. It looks like the same, similar as the previous model, and I don't think it is the same. Here's his, well, you see there's no C1. I think he had C1 written on these. There's no C1 on these. Kind of cool. He's predicting, I think, the path with the blue ink, the blue marking, or whatever color you see it as. But I would say it would crack off here at 45, right? Here and here. And there's this point loads, roller. Appears to be roller. Now he's applying the loads. Well, they're applying the loads. So we got to bear with it. We're gonna let this play out. So flexural. This is the flexural. Yeah, flexural failure reinforcement concrete beam flexural strength concrete laboratory test. That's on the YouTube channel. This is where the predicted path would be. Apparently, is where he's predicting the path to be, or the students are. And there we have my 45-degree angle. So even though it's set up to fail in flexural, I think this might have been shear first. Oh, did he just point to the left too? And then up in the middle. Cool. Here it is right there. And you can go through the video yourself. And there's this crack. And there's this one. This is his flexural one. So he probably doesn't have stirrups in here. It's going to fail faster without the stirrups and the some reinforcement to probably cross there, so he can, predict to make it happen without it failing in shear first and just brutally cracking onto the ground floor, whatever the setup is. Cool. There it is again. There's that one. Let's let this roll out. It's only not another minute. And there we go. Inbound of the support and inbound of the support, symmetrical. Again, we don't see it at the top though. You don't see it happening at the top first. And this looks like it's in plane. You wouldn't even think it was out of plane. In other words, no surface cracks are developing. They're not showing that, but that's the way I see it as. Oh, perfect. Look at that one. Right up where they predicted. He just balanced the span, loaded it, and with no stirrups, I think you would get this result. Just some transverse steel. And now this side would be starting to compress against itself. That gap, it looks fully developed. This is never going to compress against itself besides up here maybe. And, well, I won't say never, but right about here, this will start acting on itself. But will this start opening up next? This is opened up this far. Will it now get symmetry and open the other side? This is the other side I'm referring to. Oh, we're getting compression up here. Now it's starting to break through. Wow. Beautiful stuff. Beautiful. So we're getting this bow that doesn't seem like much is obviously present, and it's compressing against itself. Beautiful. And maybe the rebar is now reacting and there it pop. Beautiful. Look at that opening up. It still hasn't developed yet fully. Well, if it fails fully, then it's developed fully, isn't it? I was hoping this would open up. All right, there's Dr. Patel right there. With right, awesome. There's the other one, laboratory experiment 450. Okay, cool. Click that. Structure failure. And again, I've got it down the decking. At the beam where the beam connects to the column. In this case, our beam is the entire truss system, save number 12, not number 12. So the canopy and the bridge deck are part of the beam, and as they call it, an I-beam, if that helps you out at all. And so you can imagine the shear would happen at the deck where it meets the pier, the column. And it's what appears to happen. Then the dead loads of the structure was the force.